Happy Republic Day. This is recorded on 26th January 2025, 76th Republic Day of Union of India. Good. Okay. So this is the 27th session on measure theory and 10th and possibly the final session on Lebesgue integral. Today what we are going to talk about is one of the most important tools in integration theory. And see, in integration, when you want, as you know, computing integral is very difficult. There are only very few tricks. One is change a variable or substitution principle, as you call it in higher secondary. And second thing is perhaps integration by parts. The third thing is what we are going to learn, that is differentiation under the integral sign. Okay, this is due to Leibnitz, so it's usually referred to as Leibniz rule for differentiation under the integral sign. I'll have a lot more fascinating story about this at the end. Hopefully I will remember. Okay, I don't want to start now. It's okay. So let us get started. Sorry, I was searching for the pen. So the first situation is the following. Okay, we will talk about integrals that depends on a parameter. Okay, don't get vexed, it's very simple. Suppose I have a measure space x b mu, okay, and T is any set. Okay, for the most important thing is T usually will be an interval, a subset of R, an interval. One thinks of as a time. Okay, something like A to B at time T kind of thing. And for our thing, what we are going to do is, for the theorem, I am going to assume T is a metric space. Okay, and F is a function from T cross X to R. Okay, and that means F of Tx for each X, T and X here, right? One usually thinks of this Ft as a parametrized family. Parametrized family of functions. Functions on X. And T is called the parameter. And you can see that's why we will think of this as a time parameter. Okay, so for each T, Ft of X by definition is F of Tx. Okay, I wrote Ft without even explaining. Okay, that means for this. Okay, therefore this Ft for each T in T is a family of functions from X to R. Right, let us assume for all T this is measurable, and actually we will also assume it's integrable. Ft is in L1 for all T in T. Okay, right, now therefore I can integrate a function. I will get a function phi of T by integrating this integral of Ft of X du mu X for X capital X. This is nothing other than F of Tx fixed T and integrated with respect to X. That's what it means. Okay, I get a function. So I want to talk about the continuity of F. Continuity of phi. Right? So fixed point T naught in T, I want to say phi is continuous at T naught, but then without any kind of assumptions about the way my function F as a function of T behaves, it will be difficult to see. You see what I mean? I assume as a function of X for each T this is L1. Then for each X in X, I have to say how this function behaves. Right, for each X. then only it makes sense of something to do continuity. So what we are going to assume is that we are going to assume that for each x in x, okay, the function t going to f t of x is continuous at x naught. If you want to think of this fx, okay, then fx of t, then t going to fx of t, ft of x, this is continuous at t, right? So this is what we want to prove. Okay, using this we want to show, using this assumption we want to show phi is continuous at t naught. Yeah. So let us formulate the result, call it a lemma. What does it say? Let x be a measure space. T a metric space. Okay. Let f from t cross x to R be a function. So that what are the things I am going to assume? The first thing is for each t in t, ft of x, which is defined to f of tx, is mu integrable. That means ft belong to L1 of, okay, and 2, therefore in particular it's measurable, okay, t, each ft is measurable and it's mu integrable. When I say mu integrable, it's part of the deal, okay. The second thing is for each x in x, okay, the map t going to f of tx is continuous at some t naught in t. Okay, then define phi of t to be integral of ft of x d mu x over x, which is same as integral of f of dx dx, so d mu x over x. Okay, so this is what you call parameter dependent integral. That is the integral depends on the parameter t. Alright, for each t I get an integral. Okay, then conclusion is then phi is continuous at a t naught. So this is what you want to prove. Okay, this is what we want to prove. Let us try to embark on your proof and try to see whether we can do or we have to impose any further condition on the parameterized family. Okay. So let us start with the proof. Okay. Now let us look at T naught. Okay. Then we have, let Tn be any sequence in T so that Tn converges to T naught. Right. Therefore, it's to prove continuity of phi at a t naught, what you have to do is for every sequence Tn in T so that Tn converges to T naught, we have to prove phi of Tn converges to phi of T naught. Right? So what does it mean? This means integral of f of Tn x d mu x converges to integral of f t naught x d mu x over x. Right? Now notice that this is a sequence of functions. Okay, for each t fix, okay, the function ft is measurable, right? Therefore, if I call fn as fn of x to be as f of t and x, then fn's are measurable. And where does fn converge? Fn of x converge to f of t naught of x. Yeah, for each x, this is what happens. Because for each x, the function, again, please understand this kind of thing. for any fixed x, next the function t going to f t x is continuous at t naught, right? Therefore, when Tn converges to T naught, then f of Tn x converges to f of T naught of x, right? So that means fn of x converges to f of T naught of x, if you want to call it f of T naught of x. Okay. Now I want to say integral of fn converges to integral of f of T naught, f suffix T naught. Okay. This is what I want to prove. So that means I have to use some kind of justify this limit. Okay, what are the things which you usually have? One is monotone, which we don't have because we do not know anything about positivity or something. There is nothing like increasing sequence, nothing. Okay, and therefore the only thing is either dominated convergence or Fatou's lemma. But in any case, so therefore okay, here the idea is assume that ft is dominated. Okay, the ft is a family. Okay, t and t is dominated by some g in L1. What does that mean? That is, so this is the third hypothesis I have to make now. Okay, so third hypothesis, there exists a g in L1 such that for all t, mod ft of x is less than or equal to g of x. Of course, g is positive by very construction, non-negative at least. Okay, then what we have is this fn of x converges to f of x, ft naught of x, right, pointwise, and the sequence fn of x is dominated by g of x. Therefore, by dzt, we conclude integral of fn of x d mu x converges to integral of f of t naught of x d mu x. But this is nothing else than phi of t naught, and this is nothing else than phi of tn. Therefore, phi of tn converges to phi of t naught. Yeah. So hence we conclude that phi is continuous at t naught. Okay. Right. The next result is a Leibnitz rule. Leibnitz Leibnitz rule. Okay. What does it say? It roughly says the following. Suppose my t is actually some interval ab. Therefore, right, so my function is f from some ab cross x to r. Okay. Then assume f is differentiable as a function of t. Function of t for every x in capital X. That is fix x in x. Look at the function t going to f of t comma x. Then this is differentiable on ab. Therefore, I can denote by f dash of tx. Notice that if f dash of tx is nothing other than df by dt at tx. It is derivative only with respect to tx. Okay. Is that clear? Right. So let me do as we did earlier. Suppose I define this integral of f of tx d mu x. Now notice that phi is a function from ab to r. So that means I have to make sure these are all integrable. I'm not, okay, we will put the conditions slowly. I want to say what the theorem says. Therefore, what it says is this function is differentiable, and therefore I can, and I want to say derivative is nothing other than df by dt of at tx d mu. Okay. Loosely speaking, what it says is d by dt of the integral f tx d mu x is, I can interchange the differentiation and the integral. Push the differentiation under the integral sign. df of f of t comma x d mu x. This is what it says. Okay. This is what the theorem wants to say. So naturally, what are the hypotheses we have to look at? Okay. First, notice that this has to make sense. Okay. That means, as earlier, for each t in t, I can assume ft is in L1. These are all integrable. Okay. Second thing, this has to be different. Again, integrable, because this integral should make sense. Notice that we already know this is measurable as a function of x. For each t, this will be measurable. We will recall the proof if you need. Okay, it's exactly similar to the way we did. We will do that. Okay, then I have to say it's measurable and then integrable, and this integral makes sense. Therefore, these two integrals are the same, right? And even to prove continuity, we already assumed the third condition, namely domination. For each t, mod ft must be continuous, right? Here, what are we going to do? We are going to talk about this one. So something has to be dominated by some g. But what is that? You understand the question? 3 has to be carefully formulated. Okay. This is just to make you think. Okay. And after this, you read any book, and you will see that the proof will be in 4 or 5 lines only. Okay. Yeah. So this is a theorem. Okay. So let t be equal to some interval a, b in R. Okay. And x b we measure space. Okay. Let f from t cross x to R be such that, what are the assumptions you want to make? The first thing you want to make sure that for each t in t, the function ft of x is integrable. Integrable, this is a function of x, therefore it's integrable in this measure space. That means mu integrable, right? And 2, for each x in x, the function t going to ftx is differentiable on ab. Okay, with the derivative, let us call it's a notation with the derivative df by dt of dx. Notice that if my x happens to be something like Rn or R, then I may like to do, then it becomes a function of real variables, right? Maybe vector variable x comma y or something, or t comma x. X is also a real variable. Then I would like to write it as del f by del t of dx. Okay. Okay. In this case, this is a notation, right? Now there is a third condition about dominancy. Okay. What kind of dominancy I have to impose upon? Okay. All right. Let us go through the proof. Okay. So what we want to do, we want to say, okay, then we want to say, if let phi of t as usual be earlier f of t comma x d mu x over x, therefore this is phi is a function from a b to R. Because these are all integrable, therefore this will be real numbers. Therefore it's a real valued function. So what we want to say is phi is differentiable, and we have, okay, phi dash t is integral df by dt of x at t comma x d mu of x in, okay, or sometime del f by del t comma x d mu x over x. Okay, so I have to make sure this is also integrable. Okay, on the way we want to prove integrable. Okay, so this begs a question: is this measurable? is integrable. These are the questions we have to make sure in our proof. Okay, right. Now let's see how to do that. So now what is phi dash of t? Phi dash of t, suppose Tn is a sequence which converges to t in AB, in the interval AB, or Hn is a sequence which converges to z, therefore my Tn may be t plus Hn, but this has to be in AB. Hns are chosen so that t plus Hn, namely Tn, must be in AB. Then phi dash of t by definition, okay, or let us even look at f first. Okay, phi dash of t, if at all it exists, it must be phi of Tn minus phi of t by Hn, where Hn is t minus Tn. Okay, and this limit t goes to n goes to infinity, or Hn goes to 0. In this case, the same as n goes to infinity. Right? It is for any h, but we want to choose sequence. Why? That is because we can see this. This will be. We want to talk about measurability of this and integrability of this. So we want to do that. Okay. Let us go slow. Let us look at various things. So let us look at f of Tn comma x minus f of t comma x by Hn. Remember, my Hn is t minus Tn. That is, or Tn minus t. Because you usually write f of x plus h minus f of h x by h. So I am writing that notation. Therefore, Tn minus t. Okay. Right. So this goes to df by dt at tx. Is that clear? So what we want to do is, when I want to show this phi is differentiable, I want to look at phi of Tn minus phi of t. That is, I want to look at phi of Tn minus phi of t by Hn. Okay, that goes to whatever is the integral df by dt t comma x d mu x. This is what we want to show. You follow that? Yeah? Yeah. Therefore, so what do you want to do? I want to look at a sequence now. See, I want a convergence, and these phi t's are defined by means of integral, right? Therefore, what I want is integral of a sequence, okay, limit of the integral of a sequence equal to integral of the limit. That's what we want to do. Okay. So let us try to formulate it. This. So let us look at my fn of t comma x, or f to be f of tnx minus f of tx, okay, by hn. Again, hn is tn minus t, right? So as n tends to infinity, then where does f and tx goes to? A point wise it goes to del f by the derivative of d by dt, derivative of f with respect to t at point tx, right? Therefore, this is point-wise convergence. Okay. Therefore, what I want to do is, let us look at integral of fn tx, okay, d mu x over x. This is nothing other than phi of tn minus phi of t by hn. Is that clear? Yeah. So I want this sequence converges point-wise. Therefore, the integral converges to this integral. Okay, integral of the limit. Okay, this limit will be equal to integral of the limit. Okay, so I want to say limit of integral f and tx d mu x, which is nothing else than this fellow. Okay, limit of phi of tn minus phi of t by hn. Okay, this goes to integral of this limit. This is df by dt of t comma x. Okay, so as I argued in the earlier lemma, so I need some kind of dominancy. Okay, I have to dominate these fellows. So what should be my domination? See, notice that Fn are all in terms of Ftn minus Ftx by Hn. You understand? So earlier in the lemma, I needed the dominancy of only Ftx. Here it is difference quotient. Okay. Now what kind of dominancy I have to have? Remember, yeah, whenever you see such things, this kind of difference quotient, you should remember mean value theorem. This fellow is nothing other than some f dash of some xi and x, where xi depends upon this n, okay, and also x. Okay, but let's not worry about it. It's f dash of xi x. Therefore, if I know have a domination for this, I'll be happy. Okay, so let's go back. So what is the third condition I want? Third condition I want is the following. Okay, there exists a g in L1 says that for all t in t, df by dt, this df by dt at tx is less than or equal to g of x for all x in x. Okay, right. So we are now ready for the proof. I hope don't be discouraged. Usually, as I said in my about the channel, I'd like to think aloud. This is the way I think when instead of writing down everything from memory, you write down the statement, from memory, you write down the proof, explain line by line carefully. Mathematics is correct. Whereas I want to see how to do that. Okay, don't be put off, but you think like this, it will train you how to solve problems, other problems also. And furthermore, it will make you understand how to read a theorem and its proof. What are the questions to ask? Okay, that is the way you can master the thing. Okay, this will also help you to write the proof carefully, much better. Okay, after doing this only, I will write a careful textbook proof. You might have seen many times in my real analysis course. So let Tn be a sequence in AB such that Tn converges to T0. Right? Then let us consider phi of Tn minus phi of T. For every sequence, I am going to show this is Hn. Let Hn be equal to Tn minus T. Okay, this converges to. Okay, we want to show this df by dt at t comma x t mu x. Okay, but what is this fellow? This fellow is f of Tn x, okay, minus integral f of tx, and Hn is common, therefore 1 by Hn. Okay, this is d mu x. I am not, but right, but this is nothing other than integral of. Are you following? Phi of Tn is this, phi of t is this, and divided by Hn by, notice that by, remember by assumption these are all integrable. Therefore, by the algebra of integral function and linearity, this fellow is nothing than f of Tn x minus f of tx by Hn. And d mu x. Okay. So now I have a sequence of this function. Right? Now what do I know about this sequence? If I call it as phi fn of x, okay, these tn's are all fixed now. So f of tn x minus f of tx by Hn, okay, These are all measurable. And this one converges to df by dt at dx. Okay, therefore this is also measurable. So we proved it. This is also measurable, right? The next thing, by assumption, by 3 df by dt of dx is less than or equal to some g of x, right? But remember, my fn of x, which is f of tn x minus f of tx by hn by mean value theorem equal to some f dash of xi, let me call it only f dash of t, I should not use t, f dash of some tau x, where tau lies between in the interval x to x, t and tn, and also this tau depends on n and x. Remember, for each x the function t going to ftx is differentiable. Therefore, I am applying to this function. If you want, think of this as a function. This is differentiable at t naught, right? So I am applying mean value theorem to this function. Okay. Therefore, that will also depend upon x. Okay. Right. Is that clear? Therefore, this fellow is nothing other than f dash tau of x. Therefore, mod fn of x is less than or equal to mod f dash of tau x, but that's less than or equal to g of x. Therefore, what I have shown is my fn's are dominated. Okay, therefore fn's are dominated by g, and fn converges to df by dt pointwise. Therefore, hence by dct we conclude, okay, this pi of tn minus pi of t by hn, okay, it converges to integral df by dt at dx dmu. Since it converges, therefore this is differentiable. Therefore this is differentiable, and the derivative phi dash of t is df by dt at t comma x dmu x. Okay, so pause, review, proceed. So the proof is over, but somehow it's very strange. I was so carried over thinking aloud, I didn't say pause, review, proceed. Okay, I should have done it after the lemma, after justification of how the dominancy comes. I should have asked you to pause and review. I'm sorry, sometime I'm not in my form, I don't do that. Okay, now this is what you have proved. Now we are going to talk about some applications of this. Okay, so as I said, to evaluate integral, there are essentially three methods. One is substitution or change of variable. Second thing is integration by parts, that's usually to estimate. Also, the third thing is using Leibnitz rule. That is, you will get an integral of a function, then introduce a parameter. Okay, think of the function as a one particular function in a parameterized family, and then somehow apply the differentiation, that is Leibnitz rule of differentiation under the integral sign to compute the integral. It all looks mysterious because these are the things which are never brought out in a typical course, because only theorem proof, especially in master's degree, lot of theory, they want to finish that. Okay, but this is very, very powerful tool. Okay, I will just explain what the problem we are looking at, and we will do preliminary work and then complete the proof. So the application I want to do is this. This is, those of you who have seen something like a gamma function, you will know that e power minus dx, it will be some factorial, maybe n factorial. Okay, maybe. Okay, I am not sure, but we will see that later. Okay, you want to prove that. Yeah. So the trick is very interesting. This is what you want to show. You want to compute this null and show this. The trick is to show the following. That is, I want to integrate e power minus x dx from 0 to infinity. This is very easy. You know that this is integrable. Okay. Right? Because this, since e power minus x is a non-negative, therefore if I look at fn of x to be u power minus x into integrated function of 1 to n, okay, that fn increases to f, right? Fn increases to f. Therefore I can use monotone convergence theorem. Then when I want to compute integral of fn, that's very easy. This is 1 to n u power minus x dx. Okay, but Lebesgue integral, since this function is continuous, this Riemann integral exists and Riemann integral is Lebesgue integrable. Therefore, this fellow is nothing other than 1 to n of u power minus x with respect to dm of x if you want, right? But to compute, we had already proved fundamental theorem of calculus. Therefore, this is nothing other than e power minus x, okay, minus I u power minus x between 1 and n, which is 1 and, sorry, 0 and n. I forgot 0 and n. I am dealing with 0 and n. 0 and n. This is going to be 1 minus and plus e power minus n. As, okay, as n goes to infinity, it goes to 1. Therefore, this e power minus x is differentiable. Please go through this. So, when you want to do Lebesgue integral, how are the things I have proved? E power minus x is first continuous, therefore different measurable. Then I want to compute this integral. What did we do? We looked at this as a sequence of fn, but this fn integrability is very easy because these are all continuous. We used Riemann integral is the same as Lebesgue integral, therefore I can compute by Riemann integral. But to compute the Riemann integral, I can use fundamental theorem of calculus and then pass to the limit by monotone convergence theorem and all that. Okay, this is very beautiful, very simple. But instead of simply saying e power minus x is e power minus x between 0 and infinity, therefore it's 1. Okay, this is the standard proof. Okay, non-rigorous, but you understood this, right? Okay. So the idea is to do this way, 0 to infinity e power minus dx. dx. Now t is the parameter. T is positive. Okay, some parameter, right? Are you following? This again, by the same logic as above, argue as above, then denote fn of x to be integrated function of 0 to n. I wrote 1 to n earlier perhaps. This means 0 to n, sorry. Okay. So 0 to n of fx, where fx is ftx if you want, which is e power minus dx, or simply say e power minus dx. Now this again I can compute. This is going to be 0 to n e power minus dx dx. This is with respect to x. Please remember this as a primitive, namely the primitive is e power minus dx by minus x minus d, right? And this is x equal to 0 to n. Therefore it's going to be, I hope I am right, it's 1 by t. Okay, therefore this is again integrable. We found it. Okay, this is for true, any for t. So we found it. Is that all right? Okay. Now what I want to do is this. Therefore, if I look at my phi of t to be integral 0 to infinity e power minus dx dx, this is the same as, remember in Lebesgue notation, this is 0 to infinity e power minus dx dmx. We proved this. Okay, this integral exists. It is nothing other than this integral. Okay, this is the definition of improper integral. Okay, and this is the definition of Lebesgue integral. And what we did was, at each 0 to this sequence fn converges to, in fact, monotonically increases to f. Okay, therefore I can use monotone convergence theorem. Okay, are you following? This is 0 to infinity e power minus dx dmx is equal to limit of integral fn, okay, over 0 to n. Okay, this is actually Riemann integral 0 to n of e power minus dx. This is the limit. That's all it. But this is the definition of improper integral. Limit 0 to infinity of e power minus dx. I'm sorry if I get bored, because many of this kind of analysis never done. As I said, I computed e power minus t 0 to infinity. I simply said e power minus t minus of that between 0 and infinity. Substitute, you get the result. Okay, that's how usually it's done. Okay, so I just wanted to change that. Okay, how to do analysis carefully. Okay, I hope you appreciate and you came to my channel to understand analysis. Otherwise, these are all, very boring details. If you are formally manipulating symbols. Okay, right. Let's come back. Right. So what I have done, the next thing you want to say, these are integrable. The next thing I have to show is, let us look at this function f of tx, which is e power minus tx. Therefore, what is the derivative df by dt of tx? Notice that this is with respect to the derivative, therefore it's minus x e power minus tx. Right? So I have to, if I want to apply Leibnitz rule, what I have to do is I have to say this is integrable. This is integrable for all t. Okay, this is a question mark. Okay, so that's where the Leibniz rule comes. So I have to apply, as is, I have to find some f such that df by dt of dx is less than or equal to g of x, where g is integrable. Right? You follow that? Right. Notice that again, if you go back, my original thing is I want to talk about x power n. Okay. Therefore, I have to keep differentiating this. If I differentiate e power minus dx, you saw minus x. If I differentiate once more, I will get minus x squared and so on. Right? So, roughly I want to look at the behavior of this function, that is x power n e power minus x, or e power minus, let us say, minus dx. Okay, this is integrability. This is this domination on 0 infinity. This is what I have to do. Okay, so let us look at a more general case. Let alpha be r and beta be positive. Let us look at x power alpha e power minus beta x, and x is greater than 0. So these are the functions defined on 0 infinity. This is a function f of x that f depends upon alpha and this. So I want to talk about integrability of this function on 0 infinity. This is what we want to look at. Okay, right. Now notice that x power alpha e power minus alpha beta x, if I look at x power alpha, we know its integrability on 0 1 and integrability on 1 infinity or any alpha infinity differs. Here I want it to be alpha should be greater than minus 1. Here I want to be alpha should be less than minus 1. Right? Okay, so one has to do little careful analysis, because notice that this will always be, since x is positive and beta is positive, this will be less than or equal to 1, therefore this will be less than or equal to x power alpha. Right? So I cannot use that, because this x power alpha, okay, integrability of this depends, the choice of alpha depends upon whether I am looking at integrability near 0 or integrability near infinity. This is how one thinks analysis. Okay. So one has to be careful. So this estimate shows, okay, this estimate shows x power alpha e power minus beta x is integrable on 0, 1 if alpha is greater than minus 1. Okay, because this function, if alpha is greater than 1, this is integrable, and this function is continuous and hence measurable. That's bounded by integral function. Therefore, we have seen a keen observation, a simple observation. This will be integrable. Is that clear? So I only have to look at now 1 infinity. So I'm going to write 0 infinity as union of 0, 1 and union 1 infinity. Right? On this integrability, if I assume alpha is greater than minus 1, integrability of this function is assured. Then I have to check this. So as I said, this will not do. What do it will not do? E power minus beta x, this is less than or equal to x power alpha, will not do to discuss integrability on this interval. Right? So I need a somewhat more delicate estimate. Now, what is the idea? I am doing real serious analysis because these are the things which are never done. Because people ask, we learn a lot of convergence theorem in Lebesgue integral. What is the use? This is how you use. You have to understand how to estimate things, function. Now let's look at x power alpha e power minus beta x. Beta is a positive quantity. Let's just assume e power minus x. Now I know as x goes to infinity, e power minus x goes to 0 much faster than x power minus n for any n. Yes, it goes to 0 as much faster than 1 by x power n going to 0 as x goes to infinity. Is that clear? That is the trick. Okay, that is the intuition. Okay, that is usually we assume because of L'Hopital's rule. Okay, now we don't want, we will prove it different way. So that means e power minus beta x will vanish much faster than 1 by beta 1 upon beta x power n for any n you choose. Right? Therefore, the power of x is going to be x power alpha into x power minus beta m. You understand that? Think of its beta as 1, just to think of x power minus n. Therefore, what do I get? I will get roughly the behavior of x power alpha e power minus x near infinity is going to be something like alpha minus n, where n could be as large as I want. Right? Now, your alpha is greater than minus 1, right? But that alpha is fixed, right? Therefore, I can choose any n, for any n I said, therefore I can choose n very large. Therefore, alpha minus 1 by n, alpha minus n will be less than minus 1. Therefore, it should be integrable. This is the how a typical analyst thinks. Then one wants to write this as in terms of rigorous way. You understand this? If our analysis is weak, this is a very good thing. Please go back, learn it, and pause it, discuss with your friends. So what we want to do is we want to estimate x power alpha e power minus beta x, right? So remember, I had convinced alpha is minus 1 because of the first condition. Okay, integrability on 0, 1. So I am going to stick to that. Now what we do is let's look at e power beta x, right? This I want to say is less than or equal to some x power alpha minus capital N, where n could be as large as I want. Therefore, this will be less than minus 1, right? Alpha minus n will be less than minus 1. Therefore, integrability is assured. At infinity is assured. Okay. Then let us look at e power beta x. We know is beta x power n by n factorial n from 0 to infinity. Therefore, this is greater than or equal to beta x power n by n factorial for any n. Right? It's actually strict, but let's not worry about it. Therefore, e power minus beta x is less than or equal to n factorial by beta power n into x power minus n. Right? This is true for any x in, okay, and for any n this is true. In particular I can choose. Therefore x power alpha into e power minus beta x will be less than or equal to n factorial by beta power n. This is a constant times x power alpha into x power minus n. So if I choose n very large, alpha minus n will be negative or less than minus 1. Therefore x power alpha e power minus beta x is integrable on 1 infinity if you want strict 1 if alpha is greater than minus 1 and beta is any positive. Therefore what you are shown is x power alpha e power minus beta is integrable on 0 infinity if alpha is greater than minus 1. Pause, review, proceed. Okay, now the end of the tunnel is clear. Because what did we have? We looked at phi of t to be 0 to infinity e power minus tx dx. Right? Then my f of tx is e power minus tx. Therefore df by dt of x dx is going to be minus x e power minus tx. But we know this is integrable by whatever we have seen just now. Right? Therefore Leibnitz result can be applied. Therefore integral of e power minus tx dx is my phi of t and phi dash of t. Okay, we know this is nothing other than minus 1 by I think 1 by t, right? 0 to infinity. Okay, phi dash of t is minus 1 by t square. Yeah, but then this is equal to e power the derivative of this d by dt of e power minus tx dx. But this is d by dt is this is again 0 to infinity minus x into e power minus tx dx. Right? I don't know whether I made some mistake. So this is a minus sign. Okay, this minus sign will cancel. Therefore you have shown that 0 to infinity of x e power minus tx dx is 1 by t square. Therefore when I take t equal to 1, what I get is 0 to infinity of x e power minus x equal to 1. So now do induction. Okay, then what will be phi double dash of t? Remember what I will have is this. This I can again is integrable. Therefore I can differentiate. Okay, exact. Okay, by repeating the argument x power alpha e power minus beta x, alpha greater than minus 1 is good enough for me and beta positive. Therefore all these derivatives, okay, my ftx will be, now new ftx will be x into e power minus tx. Therefore you can differentiate, show that df by dt new for d by dt will be L1 and keep on doing. Therefore I will have derivatives of d by dt power n of this. Okay, that will be something like n factorial by t power n or something, and put t equal to 1, you will get the result. Okay, so pause, review, proceed. The last one I didn't try to rigorously prove it. Okay, you have phi of t, then try to find the second derivative, assume by induction, nth derivative, etc., and make use of the observation we did. Okay, these things can be proved. But whatever I done even up to the first one, already taught lot of things. How to use various convergence theorems. Okay, that is why I did that. Because many Lebesgue integral course, they just prove in a 4-line proof Lebesgue's rule of differentiation under the integral sign, but they don't really try to give what are the applications and how we thought of it, what kind of conditions we impose, why we impose such conditions. These are all very interesting. And that's why I proved the lemma. For the lemma, the dominancy was different. For the Leibnitz rule, dominancy has to be carefully formulated. We did that. Okay. Once you understood, then we are appeal to mean value theorem. Please go through this. Enjoy the proof. Don't worry about line by line. Enjoy the proof. Then if you want, read any book. Hi. I signed off. This is appended later. I just said there is a very interesting thing about Leibniz rule, which I wanted to share. See, integrating to compute the integral, you introduce a parameter and use Leibniz rule and got it. I showed an example just now, right? This is a very, very useful technique, and mathematics it has been used many times. Okay, some other, for example, one of the things is Gaussian integral. That's also done like that. Anyway, this is a very standard trick, but the trick has been very popularized, very much popularized by Professor Feynman. Okay, those of you who have not seen, I'll just write down the name. Maybe Dublin, I'm not very sure. I think it's England. Okay. So Feynman was very, very fond of computing integrals using this. Whenever you want to compute some definite integral like this, you will introduce a parameter, okay, and then use Leibniz rule. And if you do a Google search, you will find, if I remember right, there was an article about some 4 or 5 examples were worked out using this trick. They usually call it Feynman's trick. And there is also a YouTube video sometime, okay, looking at some horrendous looking integrals, okay, which can be computed using this Leibniz rule trick, but then Feynman's trick as they call it. Okay, please have fun, watch it, look for it. You may find one or two, and you may find it very interesting. Thank you. Okay, I hope you will continue to watch me. Okay, you are not put off by this kind of thing. Okay, thank you very much. We will meet again. Take care. And once again, happy Republic Day.